AP Chemistry students, this is the Learning Objective 1 question that we worked on in class today that we did not have time to get through. And so I want to show you how this works. Although most of you did a really good job identifying the main parts of this, there were a couple of mistakes that several of you made that I want to make sure is clarified. First of all, we have this magnesium and hydrochloric acid reaction, so let's make sure that that is written out. Magnesium plus hydrochloric acid makes magnesium chloride and hydrogen gas. Now the important part here is this hydrogen gas. That is the only gas in this equation, so in terms of our moles, it's the hydrogen gas that matters, nothing else. And remember that when we deal with energy, which is equal to heat plus work, and work is equal to negative pressure times the change in volume. We're only looking at gases for that change in volume. We can also say that work is equal to negative N delta N RT. So we can do this a couple different ways. And we are given a pressure here, which is important to note. It's at constant pressure, so that is important as well. And why it's important is it makes this a true statement. And so we can plug in either one of these equations, the negative pressure times change in volume in for work, or the change in number of moles times R and T. And so if you want to use this equation, you will need the pressure. If you're going to use the other equation, you don't need that pressure. And so I'm going to use this one instead because it already includes some extra work that maybe I would have to do. All right. Oh, and I should say then that Q is given to us. That is our heat. Notice that it says the heat is released, so that means that this is a negative value, negative 500 joules. And we need to get work in joules as well. And there's a couple different ways to do that. I'm going to show them both here in a second. So we need to calculate work because we have energy is equal to negative 500 joules minus whatever we have. So we have work is equal to negative the number of moles times R, which is going to be 0.0821, and then times temperature, which is 325 Kelvin. So we need to get this change in number of moles. Again, the only gas that matters here is on the product side, which is that hydrogen. So it's going to be however many moles of gas we have on this side minus how many moles of gas we have on this side. Magnesium's a solid, hydrochloric acid's an aqueous, and this is also aqueous. So we're going to figure out how many moles of hydrogen we have here, take that minus how many moles we have on the reactant side, which is 0 moles of gas. And so whatever moles of the hydrogen we have is the moles that we plug in for a work equation. So we have down here 25 grams of magnesium, 24.3 grams of magnesium is 1 mole of it. Let's get that mole ratio. We end up with an answer of 0.0103 moles of hydrogen gas. So work is equal to 0.2748, and that is liter atmospheres. The reason why it's liter atmospheres is because this is in moles this is in Kelvin, and this is in liter atmospheres over mole Kelvin. So the moles cancel and the Kelvin cancel, so we're left with liter atmospheres. We can convert this then. That's 27.8 joules, and I started out here with that negative sign here, so there it is, my negative. So that needs to carry through to my answer. So here's my negative 27.8. So we put this in here, negative 27.8 joules. I apologize for this. I don't know why this is a negative here. This should be plus. So we have our 500 plus a negative 27.8 joules. This is equal to negative 527.8 joules as our final answer. Now I wanted to show you this step again here, the work here just a little bit differently. What we can do instead is do the negative 0.103 moles times 8.314. This is another R constant, and all we're doing here is we're taking our 0.0821 and doing the conversion there, the 0.021 liter atmospheres per mole Kelvin times 101.3 joules. So that gets us joules per mole Kelvin times 325 Kelvin. And we have there. And so we end up with the same work here of negative 27.8 joules. And that just saves a step, I guess, because this constant is given to us whenever we deal with R constants. So really, anytime we see a problem where we have joules in it and we're dealing with gases, use this constant as opposed to the 0.0821, because you have to do an additional conversion here. You could have also used this one here and used the ideal gas law to solve for the change in volume and multiply that by pressure. You're still going to come out with the same thing, negative 27.8 joules of energy. And so there you go.